Okay, so in this video we're going to do a couple example problems showing how we can use these polynomial approximations to kind of make some progress on this. Now, if the last video was a little confusing, I'm sorry about that. Hopefully this will clear things up here. Let's first kind of give the general result here. So remember our linear approximations. Let's just go ahead and write one down for like L3. Because what we determined here is that we could write this as, and L3 just means it's a third degree approximation. And what we could do with this here is we would write this as f at a over 0 factorial times x minus a to the 0 power plus f prime at a over 1 factorial x minus a to the first power plus f double prime at a over 2 factorial x minus a squared plus f triple prime at a over 3 factorial x minus a to the third power. And then we talked about you could add a fourth or a fifth on. Let's do another example just to show you how this works here. Now, I also want to mention here, A is called the center of your approximation. And the reason we call it the center is that you need to be close to it on either the left or right hand side in order for the approximation to be accurate. Because on the graphs we drew the other day, we said as further away you get from the approximation, the worse the approximation becomes. Okay, so then let's go ahead and look at another example here. Let's look at this one here. Find a quartic approximation to e to the x using a center of a equals 0. So remember here, because I'm doing quartics, I'm going to need 4 derivatives. So I'm going to just start with f at x, and remember this is kind of my 0 derivative, is e to the x, and then f prime at x, well these are easy, this would just be e to the x, f double prime at x would also be e to the x, f triple prime would be e to the x, and then the fourth derivative would also be e to the x. Now, there is kind of a shorthand way to write this. Finger's not making it move. There's a shorthand way of kind of writing this down, or a more compact version so that you can remember it. But on an exam, a final exam for instance, I'm going to want to actually see the polynomial, not just the shorthand notation. Okay, so now remember we have to evaluate all of these, and in this case we're evaluating them at 0. But that is actually very convenient for me, because f at 0, well that's just e to the 0, which is 1. And then f prime at 0 is 1, f double prime at 0 is 1, f triple prime at 0 is 1, and the fourth derivative at 0 is 1. Alright, so then we have to figure out how we are going to not figure out how we need to write the equation down here. So the compact version of this is that we can say the nth polynomial approximation, we start from k equals 0 up to n of the nth derivative evaluated at a. I'm sorry, not the nth derivative, this would be the kth derivative. We're going up to n, and k is our variable, over k factorial times x minus a to the k power. So what that is saying here is if we're doing a fourth one here, well, I'll go ahead and do this here. So it's f at the 0 power divided by 0 factorial x minus 0 to the 0 power plus f first derivative at 0 over 1 factorial x minus 0 to the first power plus f second derivative at a over 2 factorial x minus 0 squared plus f third derivative at a over 3 factorial x minus 0 cubed plus f fourth at a over 4th factorial x minus a, which is 0, to the 4th power. So that's what this is basically saying we do. Now, all we have to do is basically substitute in and simplify. So L4, well, this is all 1 here, and this is 1, because x to the 0 power would be 1, so we get 1 plus, well, remember all my derivatives evaluated at 0 were 1, so I have 1 over 1 factorial, which is still 1. So you'd have 1 plus x plus second derivative at a was 1, x minus 0 squared. So this would be x squared. Now you don't need to simplify the factorials out. You can just leave it as 2 factorial plus you'd get x cubed over 3 factorial plus x to the 4th over 4 factorial. Now what's nice about these is once you've done one of these, you can kind of see in a pattern, and so we could easily, just without doing any work, write down an approximation for L to the 10. This would be 1 plus x squared over 2 factorial, just following my pattern, x cubed over 3 factorial plus x to the 4th over 4 factorial plus x to the 5th over 5 factorial plus x to the 6th over 6 factorial plus x to the 7th over 7 factorial plus x to the 8th over 8 factorial plus x to the 9th over 9 factorial plus x to the 10th over 10 factorial. So you can see it's a real quick thing that you could do. Once you've done a few terms, you can see what the pattern is and just going on. But what I think is that this is a very interesting, kind of easy to evaluate thing. So I want to look at an example here with this. So this is my approximation that I'm going to do. And we're going to approximate. We'll see how good this is. I have no idea how good this will be, but we'll do e to the 0.2 power. Now I'll first just do this on my calculator, just so we know what the answer is. This is 1.221402.758 going on forever. Alright, so then let's figure out what it would be using my approximation. So L4 is equal to 1 plus x plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the 4th over 4 factorial. So L4 at point 2 would be 1 plus 0.2 plus 0.2 squared over 2 factorial plus 0.2 cubed over 3 factorial plus 0.2 to the 4th over 4 factorial. Now this is simply just arithmetic at this point, so I'm going to just do the arithmetic real quickly on my calculator. Maybe I will. I'm going to pause it. Okay, and so once I do that approximation here, I get that this is equal to 1.2214. Wow, that's pretty accurate actually. It's accurate to 4 decimal spots. Now if you wanted to see what the percent error is for these, or the error, actual minus approximation over actual. And of course you multiply it by 100 to get a decimal. So for this problem, the error is equal to, I'm just going to do this real quickly on my calculator. Apparently I'm not doing it that quickly. So as far as the error is, this is 0.000225%. So error is less than 1%. And you can kind of see that. It makes sense because it's accurate out to 4 decimal points. So if it's accurate out to 4 decimal points, you got tens, hundreds, thousands, 10,000s. So that makes sense. All right, we're going to look at one more example in another video.